welcome everybody to the 5G Winners Circle. I guess a chord off of a circle is the best that we could fit in this area. So we've got with us on stage here representatives of each of the teams. What I want to do to just get things started is give each team a couple minutes, introduce yourself, introduce the rest of your team members, and just give us a little bit of insight in how you tackled the Spectrum Collaboration Challenge. Maybe John, we'll start with you on the far end.
Okay, so my name is John Shea. I'm from University of Florida, Team GatorWings, and we won the championship, so it's a great event.
Chomp chomp.
That's right. So here are the rest of our, most of our team members are here. We have David Green, who worked on FPGA and all sorts of cool tools that helped us. We have, our team lead is actually Tan Wong. Worked on lots of PHY and signal processing stuff and collaboration and everything. In the back we have Tyler Ward. Worked on acquisition and network control and management. Raise your hand. and then Marco Menendez, our one undergraduate representative, who worked on all sorts of automation tool stuff for us. So yeah, our overall vision was just build the most agile, robust radio waveform that we could, and then try to pull in as much data about the radio spectrum and build a virtual map of where the interference was coming from, where there were opportunities in the spectrum for us to take advantage of and put our own signal, control our own power to allow for spatial reuse with other teams, control our modulation. Everything was controllable and tunable, and try to use intelligence to determine how much resources we could do so we could be competitive with the other teams.
All right, Bob.
Yeah. Hey there, I'm Bob Baxley. I'm with Team Zylinium. Roy Thompson is my teammate. He's actually off mailing our giant logo so we can have it back in Atlanta. Yeah, so our approach was to build even when we wrote the proposal like 3 years ago, to build a radio with a bunch of knobs, kind of as John was saying. You want a radio that was very agile so that you could tune the knobs on the radio using artificial intelligence and all of the input from the collaboration protocol and the input you got from the spectrum. So at the end of the day, we built this TDMA, FDMA waveform where we could allocate in time and frequency these bursts, and then we used information from the collaboration protocol to understand where the other teams were in space and in frequency. We also used spectrum sensing because we didn't really trust all the collaboration messages from the other teams. So we combined all those inputs, and that dictated where we transmitted and how robustly we tried to transmit. One of the things we saw at the end was teams were getting more and more aggressive with their spectrum usage. So it turned out the final round was more competitive than the previous rounds in the tournament. So we started cranking up our aggressiveness, and that led to what Paul dubbed as Hulk mode. We called it internally killer mode.
It's better than what you told us it was called. We had to come up with that name.
Yes, thanks for polishing that up. And so what we actually saw there was we were doing erasure coding, and we had this rateless erasure code where we could just throw out more and more bursts into the spectrum and use those as redundant bursts so that if any of them got jammed, we'd be more robust to jamming and be able to recover our packets. I think that's about it. Yeah, go ahead.
All right, Peter, how about you?
My name is Peter Völgyasi. I have from Team MarmotE. This is a team of 4 people. We are originally all from Hungary, but we met at the Vanderbilt University in Nashville, Tennessee. Since then, the other team members moved back. Peter Horvath is working from Munich, Germany. Miklós, who is the brainchild of almost everything what we have, is a mathematician in Hungary. We also have Sándor, who is working in Atlanta. He is an RF engineer. So this is an interesting mix of people. We are very good friends. We have been doing these challenges from the very first DARPA challenge, so this has been going on since 2013. We built on a very, very robust and high-performance FBMC-based modem solution that we already open-sourced on GitLab, and it's usable by itself. It's a standalone component, so you can try it out. What we used for in this competition. On top of that, we developed a nice pluggable component framework where we can experiment with very focused, I would say, limited scope predictors and AI components which make basically independent decisions on channel usage, the MCS index, the mandates that we would like to carry. So we try to, our approach was we try to compartmentalize these decisions into individual components.
Okay, so I want to start by taking us in really brief terms through the 3 years of this competition. So I want you to all mentally jump back to when this competition started, and I want you to tell us from what you thought you were going to do in this competition to where you ended up, what has changed? Bob raised his hand. I think that was to wave. I think that was to wave to somebody, but I'm now going to treat that as a sign that you want to speak first.
So what has changed between 1 and 3?
Yeah. So what changed between the idea that you had before this competition started and where you are right now?
So I actually looked at the proposal recently, and not that much changed. We had the original idea, and it actually got flushed out. We even had this aggressive mode knob in the proposal, and that ended up getting implemented. It wasn't implemented until like 2 months ago, so it took all of 3 years to get there. So that's one thing we saw. Yeah, I don't know. Over the years, it was a ton of development work to build this thing. We went from Python code to C++ code to having everything in FPGA to make it fast enough to run at 40 megahertz and handle all the data rate that you guys had. Maybe I'll.
Okay, so everything is exactly
everything
as
has
planned.
changed. Yes.
I will have a follow-up question for that first, but why don't we hear from Peter and John?
Right, we actually did exactly the same thing yesterday with Miklos. We looked at our proposal that got rejected, I guess for a reason. Because we had a good...
You showed me, didn't you?
We had a good laugh we had a good laugh at our own proposal from three years ago. So it was actually a good thing that we had to write down our ideas, even though we did not get the project. So originally we thought that we had to focus on heavy FPGA development, and we was thinking that we have somewhere in the middle we have a deep neural network which will work with the low-level RF samples and do some deep magic to make the channel selection and the mandate selection as a big monolithic black box component. And it turns out that first of all we did not use the FPGA heavily. Second of all, we ended up with very small AI components which help us to guide through in different areas, but we don't have a big kumbaya machine learning model which answers all our questions. So yeah, we changed a lot.
Okay. MarmotE willing to admit change. Zylinium not. GatorWings. John, what about you?
We were also one of those proposal teams that didn't get funded by Paul.
Again, you have showed me.
Yeah, I can admit that we were also with these two guys a member of the original DARPA Spectrum Challenge, and we're now on our 4th physical layer, basic lower level radio design. So that's one thing we changed. We went through 2 different physical layers through this challenge based on wanting to be able to fit together better with our competitors and what they were doing. And another thing is that we also in our proposal had this sort of big black box reinforcement learning algorithm, and as we went forward implementing and going through the gradual incremental development process to move forward on this project, we also tried to find small places that we could put in machine learning algorithms rather than trying to find one giant algorithm that solves the whole problem at once.
I want to focus a little bit on the AI aspect, because I do think that one thing that is different is the AI that we ended up with at the end of this competition versus, I like Kumbaya AI. I'll use that for a moment. That we sort of, I think, originally believed might work at the outset. I'd maybe invite a couple of comments on the differences between what AI we thought would work, what AI is actually working, why did we end up there, and then maybe to ask, well, what next? Can we actually, was the vision right, and can we get back to it? What do you guys think?
Yeah, I think one particular question or issue is that instead of creating, at least for us, creating AI components which made the decision, we don't have those. We have AI components which can predict a very relatively short time horizon what's going to happen with the traffic loads and the RF environment. But yes, one takeaway was that at least right now, what is a reasonable goal is to create these predictors and not trying to apply immediately an AI approach which can also drive your radio. There are other, so what are the reasons? Probably one is that we just were not good enough, or the time was not enough, so that might be part of it. Also, it's kind of, so with the AI-based decision process, you don't have any guarantees that your radio won't do anything stupid. And probably we are control freaks as well, but we did not want to give up this warm feeling that based on predicted values, it is still our handcrafted decisions that will drive the radio.
Okay, so it sounds like your design, or at least the final design, is really an expert system with years of hard-learned rules, but then augment it with little bits of AI that are feeding that expert system with the prediction values that it needs to make a decision about how much traffic to carry, what frequencies to carry it on, et cetera.
Exactly.
Bob and John, what about you guys?
Well, I think one of the issues, you look at AlphaGo and these other AIs that have solved really hard problems. AlphaGo, they can run a match in a millisecond. For us to run a match, we're pushing an image up to Coliseum, that's 30 minutes. You run the match, that's 30 minutes. You analyze it, that's 30 more minutes. So, you got 90 minutes a match. It's just not scalable to do enough matches. And then you've got the variation, in Go, you can play yourself, and, the AI you're training, they can play themselves and try to get better and better. We don't really have that dynamic. And you could kind of play yourself, but that didn't necessarily mean that you would be any good against other teams that didn't look like how you looked. And then there was such a variety of teams, and it was hard to control what team you were playing with. So there was just so many more degrees of freedom, as you pointed out in your talk, that it was hard to train, what we would think of as like an AlphaGo in this scenario, because it was just not enough data to train it. I think, very theoretically, maybe it's possible if we had a lot more data, a lot more time, and we could do things more quickly. But we're, 3 or 4 or 5 orders of magnitude too little data to do that sort of thing, I think.
That's exactly our observation too, is that we built a reinforcement learning algorithm that could turn lots of knobs, but eventually we said, well, we need to keep cutting the size of our state space smaller and smaller to have a hope to even train this, and still we were doing matrix completion type stuff with neural networks to try and fill in all the missing data. And eventually we said, well, what happens if we're overtrained for these scenarios, and then championship scenarios or something else, So we eventually backed off on that sort of bigger picture, letting the AI turn too many things. And we were surprised at the places that we did use machine learning. Like, we used machine learning to figure out which teams were we playing with, when are we playing with really good teams, and when should we be more aggressive? And so that's that's just some of the places we used it. But the need for more data is definitely an important point. You have to have a lot of training data if you're going to do something like reinforcement learning, and if you want to turn lots and lots of knobs on your radio and not just a few things. So I think there needs to be a platform that can support that, and it probably can't be emulation-based. It has to be something more maybe simulation-based.
So the follow-up here is, can we get back to that original vision? And we're starting to see in other AI domains, autonomy, self-driving cars, the ability to do substantial training on an AI in some kind of lower veracity environment. And once we've gotten a lot of road hours that way, we then graduate to a high veracity environment. Is that the kind of trajectory you guys see here, right? In order to fill out these gaps, do we need a simulator that can run super high speed but low veracity, and then eventually we graduate to a coliseum and sort of fill in the veracity gaps?
Yeah, that's exactly what we envision is something that allows us to have that, maybe have a decision engine that you can put in and train it here and then transplant it right to the new Coliseum and test it in the emulated environment. And then maybe you move it to powder and test it in the real open air RF. So that's the sort of path to be able to have more training and then proof it in more and more sophisticated, more real life environments.
Yeah, I think one of the things that we did that we're proud of was we took out the PHY and had just the reasoning engine simulatable offline so that we could run simulations. We would use log data from the matches to populate what other people were doing and then try to simulate it. That could tell us if we had stupid ideas in our expert system. I think, yeah, it remains to be seen whether you could train a more extensive AI with lots of knobs with that approach.
So we need a wireless AI gym, is what I'm hearing,
Yes.
to let us do reinforcement learning for wireless.
Yeah, I think so.
Okay, let's talk about brains versus brawn. It came up in the competition last night. At the end of the day, DARPA really started this as a competition about putting brains into these autonomous spectrum sharing systems. But I think more than once we saw that brains alone is not enough, right? You're going to act autonomously. There's going to be mistakes. And so I think we saw that brawn was also a key component. Can you guys talk about sort of your assessment of how important not just the way the radio makes decisions is, but also the waveforms, the physical layers, the medium access layers that you've had to build along the way?
Yes, so for the two first phases, it was absolutely like that. So I think we had a great success, especially in the first phase, because we already came with a very robust radio there. In the last phase, in this year, this was fundamentally different in a sense that the radio was not really changed that much, but I would say in the last 2 or 3 months, the most crucial thing that we had to come up with, and that was our expert system. Important part of our expert system is how we prioritize the loads and how we predict load patterns. So I think as much as possible the competition really shifted by the end to the brains part, and that it was less important in the final even than it was initially.
Bob, John, brains, brawn?
I think they were both very important, but you couldn't get away without the brawn. You had to have a robust enough waveform to put up with the other team's interference, and it certainly, from very early on, informed some of our decisions to say not use OFDM, where we'd have to back off on our transmit power to accommodate the PAPR of a real highly multi-carrier waveform, and to choose good coding and to be very adaptive and go to low rate modulations, and even up to the very end, within the last few weeks, we added extensive repetition in our waveform when we get in some of these high interference environments, so that we would just keep pounding and pounding and pounding those low rate data flows that were important and worth a lot of points, but maybe could easily not be able to accommodate just with traditional ARQ. So having that brawn and understanding that it was going to be an interference type environment where you're trying to get spatial reuse and maybe you don't always easily get it, I think was very important to us. But you definitely wanted to choose those channels appropriately so that you don't have bad signal interference ratios. If you have teams that are less sophisticated and less capable, you want to choose to avoid their channels so that, if they're very sensitive to interference, then you just can't afford to interfere with them because their score will drop below the bonus and then you don't score any points. So having a decision engine that could make the right choice of which channels and how much power you can put in channels was, I think, really important and, a big focus for us over the last year.
Yeah, I think that looking broadly across all the teams, it's when we presented opportunities for spatial reuse, I think it's clear that a key factor in getting there wasn't just recognizing when or where, but was also the fact that spatial reuse it's imperfect. It's going to cause some level of interference, and those of you that we're able to sort of persevere through it. It to me, the brawn, I think, unlocks a new degree of freedom, because it means that I don't have to completely steer clear of John's channel. I can actually interfere with John. I just have to figure out what amount is actually acceptable at the end of the day, as opposed to not being able to interfere at all. So maybe that leads us to an interesting next question. I think one of the things that completely surprised me in the finale was that you all seem to have an operating mode that you when you're all professional sports stars, and when you're playing a pickup game with an amateur, you guys seem to drop your level of play down. But then when you put the best of the best together, you all really seem to amp up the play. So how crucial was adding that capability of actually figuring out who you're playing with and what their level of gameplay was, so that you could sort of modulate your approach to playing the game? Bob?
Well, I think I mean, the rules were set up in such a way that you had to be pretty polite to make it to the last 5. And then once you're in the last 5, if you were polite, you weren't going to win. I gather John had a great scheme where they could figure out that they were in the top. They were playing really good teams, and that seemed to be very useful for them. So you're worried you're not going to make it to the top 5, and if you don't do that, then that's no good. And then the rules kind of flip. So that's, I think, what necessitated this idea that you had to be nice to teams that were maybe a little weaker, but then once you were against the really strong teams, you had to attack or kill or Hulk or whatever you want to call it. I mean, I'm looking at the board over there. I can recognize Erebus's Spectrum and Yellow over there. They were particularly aggressive with these super high power little burst tones that would just blow you out of the water. So you had to figure out some way to be robust against jamming like that if you're gonna win or place.
John?
Yeah, so we had a mode we called Championship Mode, and
we'll call back the team of comedy writers to help you out with.
That'd be great. Yeah, we're struggling with our superhero memes. So, but we did have a Championship Mode. If we detected at least 3 of what we considered the top 4 competition teams, then we got much more aggressive in how we use Spectrum, how we would react if some team was further from the bonus threshold, how much intentional interference we would cause to people, how many extra packets we would pump into the link layer to sort of deal with interference. And I think that was critical to our win, basically, is that we were fairly aggressive all along, which probably hurt us early on in some of those earlier rounds, but we kind of knew that the structure of the elimination rounds is essentially we were always, if we got in the elimination round, we would be in championship mode, because the other teams would probably be the best teams there. So we could just be super aggressive there. Being able to identify when we're playing with the best teams and to really crank out the highest performance we could and keep the other teams from scoring too many points at the same time was definitely part of our goal.
Let's talk collaboration. How important was collaboration to your radios? If we look at the competition, year 1 it was there, but I don't think used by the majority of teams. Year 2, the teams really banded together, and I think greatly improved the collaboration, that the information that was shared between the radio systems. And I'd say it was almost a 50-50 mix of teams that were actually using it versus teams that weren't. And then by year 3, we really formalized how we required the collaborative information to be shared. So at the end of the day, how important was the collaborative information you received from other teams in helping you make decisions? Peter, why don't we start with you?
There are two aspects of this. One, I already mentioned it yesterday, that collaboration had an interesting side effect. It actually forced all the teams to come clean about some very essential data that we need to share with the others. And it also helped to drive our own decisions. So actually collaboration forced us to really sanitize and be explicit and very, very accurate of how, for example, measure our own performance, because we have to share our performance with the others. And it turns out that our own performance also drives our own behavior, or should. So getting back to the other part, what we used, how useful the information that was coming from the other teams, the performance, the actual current performance of the teams was crucial to drive our decisions. So without that, so this is a big change from phase 2 when our radios, the most important decisions in our radio is driven by basically the performance of other teams. I wish I could say the same about the spectrum usage, but to be completely honest, with the spectrum usage, we just try to have the weakest ever team in the ensemble to avoid their channels, and I think it's not an important decision right now.
Yeah, there's a few aspects. One kind of funny one is I think we were all fingerprinting the other teams based on the collaboration messages. So without that, they wouldn't have had a championship mode, and maybe the results would have been different. So what I mean by that is each team is reporting which spectrum they're using and with the power level and these sort of things, and our reports look different than their reports, look different than their reports. So it becomes fairly easy to determine which teams you're playing against based on those messages. So that was an interesting dynamic. As far as being practical, we actually had a way to just turn off. So we used the voxel reports and the performance reports and the distance to other nodes in our decision making, and we could turn that off in our radio and then play ourselves and then turn it back on. And we saw like a 50% improvement in performance when that was on. So it definitely helps you deconflict spectrum, and so that's goodness. And then yeah, seeing the performance was obviously critical for deciding when to go into aggressive mode and these sorts of things.
Yeah, for us, the collaboration information was critical because, just like Peter mentioned, we're trying to avoid the spectrum of those teams that are doing worse than us. And if teams are doing better than us and we can tolerate their interference because we're fairly robust, then we will be happy to do spatial reuse with them. And so, yeah, we would constantly be shifting our channels based on the scores that people were reporting and constantly changing how many channels we're trying to use to get, if we think a team is scoring more than us, we just keep grabbing more and more channels until we think they're not. And so having that information about the scores and the channels, which frequencies these teams were using, all of that was very critical. Also the geolocation information. And we tried to use that too because we built a spatial map that said, here's where we're going to suffer worse interference than other places. Try to choose appropriately based on where teams say they are using particular channels versus where our radios are located. So all of that was critical. And I think the SIL is a huge innovation that has come out of this project.
So no competition skates through without a number of close calls and a little bit of fun along the way. Scariest moment for you guys throughout any stage of the competition, and then sort of the most uplifting or the most fun moment throughout the competition? Come on,
Mine are super easy.
Then you get to go first, John.
The scariest moment was the first elimination round. I mean, the PE2, the first round where the scores came up and we had absolutely 0 in the first round because we hadn't actually been in any matches and you hadn't told us beforehand, was horribly frightening. But seeing us in the elimination in the first round and what we thought was one of our strongest scenarios from the free play jobs, the Alleys of Austin, was shocking and bewildering. And but then obviously winning the championship is just epically fantastic, great feeling, and a huge achievement by our team. So we bracketed it there with the competition.
Your scariest moment was the beginning of last night, and your most fun moment was the end of last night.
Absolutely.
Okay.
In one event, you took us from lows to highs.
You're welcome. Bob, Peter, any fun anecdotes?
Well, so yeah, what's kind of, so we work on these. You're working on your radio, and you run jobs throughout the day and throughout the night. So you run these batch jobs, and maybe you kick them off at the end of the night. So every morning was like Christmas. You wake up and you see if your radio got better or worse, or you get new content, new information about how well you did. So I'm still recovering from not having that morning high on my phone of the performance reports from the previous night's runs. Yeah, I don't know what else. In the last 2 weeks, we made huge changes to our radio to the extent we weren't sure it would work at all. So that was pleasantly surprising to see us not crash and burn in the first round of the finals.
Will you guys be okay without having access to Coliseum for a couple months, or will there be a withdrawal?
Why? Yeah, there's definitely a withdrawal. I think it's the Coliseum coupled with the competition, though. It's not nice. Yeah, you need both.
Peter, how about you? Scary moment?
Yeah, I mean, or probably the highlight was the first phase. PE1 was probably the brightest moment for us.
All downhill from there, huh?
All down here from there. I mean, in PE1 we won from the beginning to the end, so it was very exciting. And yeah, I would not say that the last match yesterday was the lowest point, because it was a bittersweet moment. We won and lost $1 million exactly the same moment. But yeah, I don't mind that you close down Colosseum for a few weeks. I really don't mind.
Okay, you just email me and you let me know when you need it back up, and we'll see what we can do. We're getting close to the end of our time here. I have just a couple questions left. What do you guys think is next for the future of AI and wireless? Where do we go from here as a research community? And then, how do we make it from a research community into impacting everything that's sitting out in front of us on this showroom floor? Yeah. Go ahead.
I think one of the big things that is still not happening, and probably the most important step would be, is that if you look around, basically RF oriented persons are doing the AI part as well in this challenge or currently. So I don't think that for hardcore AR persons, putting their power or their wizardry in the RF domain is already accessible. So we still need to bridge the gap. We need to open up for the hardcore AR persons, the interfaces or the way we present our data or what. So we really need to bring the AI persons into this field. And not
is it data? I mean, is that the X factor here? Because you could argue that the hardcore AI people also weren't image recognition experts, but that just happened to be the first large-scale data set that was freely available. And do we need to get a dearth of data out to the world, and we'll show all those AI people how good our problems are?
Yeah, not just collected data, but I think one inherent problem in this application, in these applications for AI, is that you don't have, at least runtime, you don't have the data at the same space and at the same time. So this is fundamentally different than image recognition or even autonomous driving vehicles, where pretty much all the data, you can take a snapshot what you can observe of the whole environment, whereas with RF you have these individual nodes, you need to collect their observations or disperse their observations in the network. So that's a big challenge for AI, a practical challenge, how you can have a semi-unified but inherently sparse view of your measurements.
All right, Bob, John, what's next for AI and wireless? Where do we go from here?
I mean, Peter brings up a great point. It's super easy to get into image recognition because the libraries are there and it's accessible. You don't need nearly as much domain expertise. I mean, it's pretty cool that you guys have open sourced your waveform. I think there's just so much more domain expertise required in RF to understand where the knobs are and how to tune them, and even what the objectives are sometimes. I'm pretty excited about, for the future, this collaboration idea. I think that hasn't really been fleshed out. So seeing that fleshed out in 5G and seeing how that makes spectrum usage more efficient is a pretty exciting frontier.
Yeah, I think there's several things, and two have already been brought up. One is the need for an ability to collect more data. So there needs to be some sort of platform that will allow us to train a more sophisticated AI than what we have now. Tying into that is this idea of making the decision engine something that can be sort of disjoint from the radio design. So if there's a way to make sort of some standardized radio waveforms, whether it be 5G NR or something else, or maybe choices of things that are available, they can sort of go from one platform to another, maybe a simulation platform to an emulation platform to an open air platform. Then that will allow people who just want to work on decision engine to sort of plug in the sort of wireless AI gym idea that Paul kind of mentioned. And then I think the third thing that's been missing is that we got really smart guys up here, and we haven't been able to talk to each other and sort of say, why is your radio doing that? and so not
that's
being
Paul's
able
fault, by the way.
to share. Well, yes, I mean that's a competition. You have to put up these walls and not be able to cross those walls and interact with each other too much, or the competition gets corrupted. So now being able to talk to the other teams and make things work together will give us a new opportunity that we haven't been able to realize until now.
Okay, with that, I think the future of AI and wireless seems bright. It seems like collaboration is maybe a really key nugget that we've created in this competition. But it sounds like we've also got lots more work to do. We've built something beautiful in Coliseum, and now we need to build its simulator compadre so that we can really accelerate where we go from here. But I want to just invite one round of applause here for our three finalist teams, top three winners. And with that, I am delighted to get off mic for the day. Thank you guys for joining us, and have a great rest of your day, everyone.